Welcome everyone. In this lesson, we will dive into the world of numerical integration using Python. Often in science and engineering, we encounter integrals that are very difficult or even impossible to solve analytically. That is where numerical methods come to our rescue. Our main goal today is to understand how to use Python's scipy.integrate package to perform these calculations. This package offers a suite of functions for various integration tasks, from simple one-dimensional integrals to more complex multi-dimensional ones, including quad for general purpose single integration, DBL quad for double integration, and others for even higher dimensions or specialized techniques. We will begin by focusing on single variable integrations, specifically learning how to use the quad function. You will see its straightforward syntax. We will import the function, define the mathematical function we want to integrate, and then call quad with our function and the desired integration limits. By the end of this session, you will be able to numerically evaluate definite integrals for various functions, visualize the integrands, and even handle functions that depend on extra parameters, such as the famous Bessel functions. This skill is incredibly valuable across many quantitative disciplines, allowing you to find areas, solve differential equations numerically, and much more. Let us start with a very basic example to see how numerical integration works in practice. We will calculate the definite integral of the function f of x equals x squared, evaluated from x equals 0 to x equals 1. Analytically, this is x cubed divided by 3, which from 0 to 1 gives 1/3. The Python code demonstrates this using the scipy.integrate module, which we import and give a convenient alias, sci. First, we define a Python function named f that takes a single argument x and returns x squared. This is our integrand. Then, we specify our lower integration limit, x1, as 0, and our upper limit, x 2 feet, as 1. Finally, we call the sci-quad function, passing it our defined function f, and the limits, x1 and x2. The quad function returns two values. The first is the computed value of the integral, and the second is an estimate of the absolute error in this result. So this simple setup allows us to quickly find the numerical value of the integral. Now let us expand on our previous example by adding some visual elements to better understand what we are calculating. We will integrate the same function f of x equals x squared, but this time we will change the integration limits to be from x equals -1 to x equals 1. The code begins by importing the necessary libraries: NumPy for numerical operations, scipy.integrate for the integration itself, and matplotlib.pyflash for plotting. We also slightly reduce the default figure size for a more compact display. We define our function f1 that returns x squared. The integration limits a and b are set to -1 and 1 respectively. We then use the quad function from scipy.integrate to compute the integral of f1 from a to b. The result, which is a tuple containing the integral value and its estimated error, is printed. More than just printing numbers, the code then generates a plot. It creates an array of x values within our integration range, calculates the corresponding y values using our function f1, and plots this curve. To clearly mark the integration region, it adds x markers at the function values at the limits a and b, draws vertical dashed lines at a and b, and a horizontal dashed line at y equals 0 representing the x-axis. This visualization helps us see the function and the area being computed. Let us consider another function for integration, this time involving trigonometric terms. We will calculate the definite integral of g of x equals the sine of x plus the cosine of x, with the integration performed from x equals -pi to x equals pi. Similar to the previous example, the code imports NumPy, scipy.integrate, and matplotlib.pyflash and adjusts the figure size. We then define our Python function g, which takes x as input and returns the sum of numpy's sine of x and cosine of x. The integration limits a and b are set to minus pi and pi, respectively, using numpy's pi constant. To visualize the function over this interval, an array of x values is generated, and the corresponding e values are calculated using our function g. These points are then plotted to show the curve of g of x. We also add x markers at the integration endpoints on the curve, draw vertical dashed lines at these limits, and include a horizontal dashed line for the x-axis to help visualize the area being calculated by the integral. Finally, the scipy.integrate.quads function is called with our function g and the limits a and b to compute the numerical value of the integral, which will be the output of this code cell. In many fields of physics and engineering, we often encounter a category of functions known as special functions. These are particular mathematical functions that have established names and notations due to their importance in applications, such as Bessel functions, Legendre polynomials, gamma functions, beta functions, error functions, and so on. The SciPy library provides a very useful submodule called scipy.special, which contains a wide array of these special functions, already implemented and ready for use. For our purposes, we will take a closer look at one specific type, the Bessel function of the first kind, denoted as j subscript n of x. Interestingly, this function itself can be defined through an integral. Formula is j subscript n of x equals 1 divided by pi, multiplied by the integral from 0 to pi of the cosine of the quantity n times t minus x times sine of t with respect to t. In this definition, n is a non-negative integer which specifies the order of the Bessel function. The images shown here illustrate the characteristic wave-like behavior of the first few Bessel functions, j subscript 0, j subscript 1, and j subscript 2. Having introduced Bessel functions, let us now see how to plot them using SciPy's built-in tools. We will specifically visualize the first three Bessel functions of the first kind, j subscript 0 of x, j subscript 1 of x, and j subscript 2 of x. We will plot them for x values ranging from 0 to 20. The code starts by importing NumPy for array manipulations, matplotlib.py/plot for plotting, and importantly, scipy.special, which we give the alias s. The figure size is also scaled down slightly. An array of 100 points for the x-axis, named z, is created spanning the interval from 0 to 20 using NumPy's linspace. Then, for each order n, specifically 0, 1, and 2, we use the function ssjv. This function, ssjvnz, directly calculates the values of the Bessel function of the first kind of order n for all the x values contained in our array z. Each of these resulting series of y values is plotted against z, and a label is provided for each curve indicating its order n. Finally, a title is added to the plot, and a legend is displayed to identify each Bessel function curve. Here is a small challenge for you to think about. We just saw code that plotted the first three Bessel functions by explicitly calling the plot command 3 times, once for n equals 0, once for n equals 1, and once for n equals 2. How would you modify that code to display, for example, the first capital N Bessel functions of the first kind on the same plot, where capital N could be any positive integer, without manually writing capital N plot commands? A useful hint is to consider using a loop, or, perhaps more elegantly in Python, a list comprehension. A list comprehension often looks like an expression involving an iterator variable, followed by the for keyword, the iterator variable, the in keyword, and then the sequence to iterate over, all enclosed in square brackets. This would allow you to generate all the necessary plot calls programmatically. There are many situations where the function we want to integrate, let us say f of t, also depends on some other fixed parameters. A good example is the integral definition of the Bessel function, j subscript n of x, which we saw is 1 over pi times the integral from 0 to pi of cosine of nt minus x sine t dt. Here, n is our variable of integration, but the function also depends on the parameters n and x, which are held constant during any single integration. The scipy.integrate.quads function is designed to handle such cases. It has an optional keyword argument named args. You can use this args keyword to pass a tuple of these additional parameters to your integrand function. So if you define your integrand function, say my underscore function, to accept t as its first argument, and then another argument that will receive this tuple of parameters, you would call quad like this: scipy.integrate.quad. My underscore function, lower underscore limit, upper underscore limit, args equals parameters underscore tuple. This is a very flexible way to perform integrations when your function has such dependencies. Let us now examine the integrand of the Bessel integral more closely. Recall that the integrand is f subscript n of x comma t, which equals cosine of n times t minus x times sine of t, all divided by pi. We will visualize this function for specific values of the parameters x and n over the integration range for t, which is from 0 to pi. The Python code defines a function f that accepts t as the primary integration variable and an args list containing the parameters x and n. Inside this function, x and n are unpacked from the args list, and the value of the integrand is calculated and returned. For illustration, we set x1 to 2.5 and n to 0, and store these in a list called args. The code then prints the value of this integrand function f at a specific point, t equals 1.0, using these parameters. Following this, it generates a plot of the integrand function f as t varies from 0 to pi using the fixed x1 and n values. The area under this curve, which corresponds to the value of the Bessel function multiplied by pi, is shaded in light blue. A specific point on the curve, corresponding to t equals 1.0, is also marked with a red X and labeled with its coordinates, helping to connect the function's behavior with its definition. Now, we will use the quad function from scipy.integrate along with the args parameter to numerically calculate the value of a Bessel function. Specifically, we aim to find j subscript n of x for n equals 0 and x equals x1, which was previously set to 2.5. This calculation will be done by performing the integration as per Bessel's integral definition. The code first redefines the integrand function f, which takes the integration variable t and an args tuple. Inside f, the parameters x and n are extracted from args, and the function returns 1 divided by pi times cosine of n times t minus x times sine of t. The args list, containing x1 equals 2.5 and n equals 0, is already defined from the previous step. The core of the computation is the call sciquad f0 nppi args equals args. This instructs scipy to integrate our function f with respect to t over the interval from 0 to pi, passing the contents of args, that is, x1 and n, as additional arguments to f. We extract the first element of the tuple returned by quad, which is the computed integral value, and store it in y. Finally, the script prints the args list that was used and the resulting calculated value Lie of the Bessel function. To build confidence in our numerical integration, it is good practice to compare our result with a known, reliable source if one exists. For Bessel functions, SciPy's special submodule provides highly optimized implementations. So, we will compare the value of j subscript n of x at n equals 0 and x equals x1, which is 2.5, calculated using scipy.integrate.quad in the previous step, against the value obtained directly from scipy.special JVs. The code first imports scipy.special as s. It then prints the value of j subscript n of x using ssjv n x1, with n equals 0 and x1 equals 2.5. Immediately after, it prints our value y, which was calculated using quad. We expect these two values to be very close, which would validate our integration setup. Furthermore, the code generates a plot of the j subscript 0 of x curve using SSJVs over a range of x values from 0 to 20. On this curve, it specifically marks the point corresponding to x1 equals 2.5 and the value SSJVNX1 with a red X and a label, providing a visual confirmation that our calculated point lies correctly on the true Bessel function curve. Let us now try to generate the entire curve for a specific Bessel function, for example j subscript 2 of x, by repeatedly performing the integration for different values of x. This means we will keep the order n fixed at 2, but we will vary x over a range and calculate j subscript 2 of x for each x. The Python code begins by setting up the figure size. It redefines our integrand function f, which takes t, the integration variable, and an args tuple containing x and n. The order n is then set to 2. An array named zar is created using NumPy's linspace, containing 50 evenly spaced x values from 0 to 20. The key part is a list comprehension. For each value x1 in our zar, it computes sciquad f0 nppi args equals x1 n 0. This performs the Bessel integration for n equals 2 at that specific x1. The results of these 50 integrations are collected into a list called YAR. Finally, pltplot xar YAR plots these computed y values against the x values, effectively drawing the curve of j subscript 2 of x as calculated through numerical integration. A horizontal dashed line at y equals 0 is added for reference, and the plot is labeled appropriately. We can generalize the previous approach to plot several Bessel functions, j subscript n of x, for different orders n, all on the same graph. Each point on each curve will be calculated using scipy.integrate.quad. The code starts by importing the necessary libraries and setting the figure size. It defines the integrand function f as before, which takes the integration variable t and a dummy argument list containing the parameters x and n. An array zar of 100 x values from 0 to 20 is created. The core of this script is a loop, implemented as a list comprehension, that iterates through n values from 0 to 4 inclusive. For each specific order n, an inner list comprehension is used. This inner part iterates through each dexy in our zar array and calculates the integral sciquad f0 nppi args equals n0. This computes all the y values for the Bessel function j subscript n of x across the range of zar. Each of these generated curves, one for each n, is then plotted with a label indicating its order. The result is a single plot showing j subscript 0, j subscript 1, j subscript 2, j subscript 3, and j subscript 4, all derived from their integral definitions. Now, let us compare the family of Bessel function curves we just generated using scipy.integrate.quad with the curves obtained much more directly using the scipy.special module. This comparison serves two purposes. It visually confirms that our repeated integration approach correctly reproduces the known forms of the Bessel functions, and it also highlights the convenience and efficiency of using the pre-built special functions when they are available for your specific problem. The Python code for this is quite concise. It imports scipy.special as s, numpy, and matplotlib, and sets the figure size. It creates the same ZAR array of 100x values from 0 to 20. Then, a list comprehension iterates through the order n from 0 to 4. In each iteration of this loop, pltplot ZAR ssjv n ZAR label equals n equals plus strn is called. This uses the ssjv's function, which directly returns the values of the Bessel function of order n for all x values in ZAR. A title and legend are added for clarity. The resulting plot should be visually identical to the one we produced via numerical integration in the previous step. Up to this point, our focus has been on single variable integration. We will now transition to the concept of double integration, which involves integrating a function of two variables, say lambda of x, y, over a specified two-dimensional region. The SciPy library offers the dblquad function within its integrate module for this purpose. The fundamental idea behind double integration, especially for rectangular regions with constant limits, is to perform the integration iteratively, one variable at a time. For instance, we can first integrate the function lambda of x, y, with respect to y, treating x as a constant, over the y limits. This results in a new function that depends only on x. Then, we integrate this new function with respect to x over its specified limits. Mathematically, this can be expressed as the integral from x1 to x2 of, in parentheses, the integral from y1 to y2 of lambda of x, y dy, all then integrated dx. Alternatively, we could integrate with respect to x first, then y. For many common scenarios, the order of integration does not affect the final result, a concept known as Fubini's theorem. Let us illustrate double integration with a specific example. We want to calculate the integral of the function x times y squared, where y ranges from 0 to 1 and x ranges from 0 to 2. If we integrate with respect to y first, the inner integral of xy squared dy from 0 to 1 is x times y cubed over 3 evaluated at y equals 1 and y equals 0, which gives x divided by 3. Then, integrating x divided by 3 with respect to x from 0 to 2 gives x squared divided by 6 evaluated at x equals 2 and x equals 0, resulting in 4/6 or 2/3. To perform this using SciPy, we import scipy.integrate as c. We define an integrand function that accepts two arguments, var first and var later. For this order of integration, y first, then x, var first will represent y, and var later will represent x. So inside the function, we set y equals var first and x equals var later, and it returns x asterisk y asterisk 2. We define the limits. x1 equals 0, x2 equals 2, y1 equals 0, and y2 equals 1. The dblquad function is then called as sci dBl quad, integrand x1, x2, lambda var first underscore placeholder, y1, lambda var first underscore placeholder, y2. Here, x1 and x2 are the limits for the outer integration variable, which is var later, i.e. x. The next two arguments define the limits for the inner integration variable, which is var first, i.e. y. These inner limits must be provided as functions. In this case, since they are constants, we use simple lambda functions that return y1 and y2 respectively. The placeholder in the lambda refers to the inner variable, y. As we have discussed, for functions over rectangular domains with constant limits, the order of integration in a double integral should not alter the final numerical result. Let us verify this for our previous example of integrating x times y squared. This time, we will choose to integrate with respect to x first over its range from 0 to 2, and then integrate the result with respect to y over its range from 0 to 1. Analytically, the inner integral of xy squared dx from 0 to 2 is x squared over 2 times y squared, evaluated at x equals 2 and x equals 0, which gives 2 times y squared. Then, integrating 2y squared with respect to y from 0 to 1 gives 2/3 times y cubed, evaluated at y equals 1 and y equals 0, which again results in 2/3. To implement this reversed order in SciPy, we slightly modify our approach. We define the integrand function such that var first now represents x, the new inner integration variable, and var later represents y, the new outer integration variable. The function body becomes x equals var first, y equals var later, return x asterisk y times asterisk 2. The limits x1, x2, y1, y2 remain the same. When calling psi dBl quad, the outer integration limits are now y1 and y2 for the var later y. The inner limits, which are for var first x, are provided as lambda functions returning x1 and x2. The numerical result from this computation should be identical to what we obtained previously. Let us work through another example to further practice using the dBl quad function. This time, the function we want to integrate is x times y plus 2 times x squared plus y squared. We will integrate this over a rectangular region where x varies from 3 to 4 and y varies from 1 to 2. We will compute this double integral in two ways to demonstrate that the order of integration does not change the outcome for such problems. First, we will integrate with respect to x first and then with respect to y. Second, we will integrate with respect to y first and then with respect to x. The code begins by defining the limits y1 equals 1, y2 equals 2, x1 equals 3, and x2 equals 4. For the first integration order, dx then dy, we define a function integrand 1 foot, where the first argument first corresponds to x, and the second argument later corresponds to y. We then call dBl quad with y1, y2 as the outer limits for y, and lambda functions defining x1 to x2 as the inner limits for x. For the second integration order, dy then dx, we define integrand 2 feet, where first is y and later is x. The dBl quad call then uses x1, x2 as outer limits for x, and lambdas for y1 to y2 as inner limits. Both results are printed, and as expected, they should be numerically identical. In this session, we have explored how Python, through its SciPy library, provides powerful tools for numerical integration. We began with single variable integrals, mastering the use of the quad function to find the definite integral of a function between specified limits. A key technique we learned was how to use the args keyword to pass additional, fixed parameters to our integrand, which is particularly useful for functions like Bessel functions defined by integrals. We also saw that SciPy's special module offers convenient, pre-built versions of many such special functions, which can be used for direct calculation or for validating our own integration results. We then extended our skills to 2 dimensions, learning to use dbl_quad for double integrals. This involved understanding how to set up the integrand and define the limits for both the inner and outer integrations, often using lambda functions for the inner limits, and recognizing that for many common cases, the order of integration can be changed without affecting the final result. Throughout, we emphasized how visualizing these functions and integration regions with matplotlib can greatly aid comprehension. These numerical integration capabilities are fundamental in many scientific and engineering disciplines, enabling the solution of problems that lack straightforward analytical answers.